Hello, Hopewell. This is Mr. Steinberg. We're today on day 3 of our e-learning. We're going to start today off with section 6. We're going to talk about what is a series and how you can evaluate a series using something called summation notation or sigma notation. Let's jump right in. No warm-up today. The vocabulary at the top of the page is what I'd like to teach you right now. The expression or the term series represents the sum of the terms in a sequence. So in the previous sections we studied sequences or ordered lists of numbers. If I use the word series, it refers to the sum of the terms in a sequence. Since sequences go on forever, I can't add all of the terms infinitely, but I can add part of the sequence together and get a sum. The way we do this is to maybe possibly learn some formulas that will help us to efficiently add up these terms together. And one way we can do this symbolically is to use something called sigma notation. This is the symbolic way we're going to use to represent the terms in our series. It's going to have a formula in it and some values that we're going to need to plug in. It uses, and we call this sigma notation because it uses the capital Greek letter sigma. We learned about the lowercase sigma last chapter in chapter 6, which represented standard deviation. This uppercase sigma means what we're going to add together our terms in our series. So it works like this. You have to the right of the Greek letter sigma a formula. So at the bottom in our two examples that I can see that are visible, the formula I would use to generate the terms in the sequence that I'm going to add together in my series fits the pattern something like 8 times the value of I minus 3. This value of I is not the imaginary constant. It's not the imaginary unit, the square root of -1. It's just a different variable that we use when we talk about series. Down here, the formula is 2 times I squared. And then we got to make sense of what are these numbers on the top and on the bottom. The letter I is really representing the word index, which tells you the location of the terms in the sequence that you're going to add together in your series. I probably would rather call this the index location of your first term in your series. I'm going to rewrite the word series at the top here. So if I see the number 1, that means down here I'm going to start with the very first term and add the first term, the second term, the third term, but I can't go on forever because I get an infinite sum. So that's why we use this number at the top here. Here is the letter K. I'm not sure you can read that very well, but on your sheet it probably is easier to read. K is the very last term for the value of your index. So we're going to start with the first term, go down to the second, the third, and the fourth, add these together until you end with the kth term. In the first exercise, it looks like we're adding together the first term, the second term, the third, the fourth, the fifth, and the sixth terms. So we will be adding 6 of these terms together. So just before I move on, just to make it clear, sigma means we're adding terms together from a sequence in something called a series. To the right is the formula for this sequence that you're going to add the terms together to make your series. This formula will have a variable in it. That variable gets substituted the values starting with this bottom value and ending with the top value. One of the things we can do is to expand our series and write all the terms out before we add them together. Eventually we're going to learn some shortcuts, some neat little shortcuts to add this together quickly. So let's work on exercises 1 and 2. Question number 1, it says we're adding together the terms from the first term all the way to the sixth term for a formula like 8i minus 3. With the 8i minus 3 are in parentheses, so that is the whole formula. This is a binomial formula. We're going to start together with our first term. I don't know if it's arithmetic or geometric, although I kind of think I know which one. Maybe you can figure it out too. Plugging in the value for the index. Our first value is a 1, so it's just 8 times 1 minus 3. Gives us our first term. Order of operations, of course, matters. 8 times 1 is 8, take away 3. That means our very first term is a 5. Our second term, plug in the value 2 for the index. 2 times 8 makes 16. And 3 less than 16 is 13. So together, 1 and 2, these are your first 2 terms in this sequence, but what makes this a series is we're going to add these together. Our third term is 8 times 3 minus 3. 24 minus 3 is 21. Now I'm picking up a pattern. T sub 4. It seems to me that each of the next numbers is 8 more than the previous term. 8 times 4 is 32, take away 3 is 29. Yep, that's right. This is an arithmetic series. 8 times 5 minus 3 would be 40 minus 3, or 37. And our last term, not the last term of the sequence, but the last term of our series. It's the last term that we're going to add together in our sum. 48 minus 3 is 45. So now if I expanded out this sigma notation, I would get a sum that looks something like this at the bottom here. I would just add together 5 plus 13 plus 21 plus 29 plus 37 plus 45, and this would represent the value of our series, the first 6 terms in the series. Add these all together, and I get 150. So the partial sum of the first 6 terms in the series is 150. We would just add these all together because that's what the sigma represents. All right, let's move on to question 2. Now, our formula is 2i squared, but I'm not starting with the first value of 1 for the index. It says I'm adding the 6th term, the 7th, the 8th, the 9th, and the 10th. Those are going to be the number of terms in our series. So starting with the value of 6. So the 6th term is 2 times 6 squared. Order of operations, of course, matters. 6 squared is 36 times 2 is 72. Then t sub 7, and t sub 8, and t sub 9, and t sub 10. Why don't you pause the video and evaluate these values? I'll just do one more with you. 7 squared is 49. So 2 times 7 squared, 49 times 2 is 98. Again, pause this video, find the next terms, and I'll be waiting for you when you return. Okay, we are back. Did you get 128, 162, and did you get 200 for the last term? So we're going to add these together. 72 plus 98 plus 128 plus 162 plus 200. Adding these all together, either with or without a calculator, gives you a sum of 660. Now this sequence generated down the side here, this sequence, I don't recognize it as arithmetic. We're not adding the same value each time. It's not geometric. It's just something different. It looks like it's a quadratic. That's pretty much how this works. Down the bottom of the page, we're going to do a couple of extra examples and one more challenge. So let's slide this down. And let's make it straight so we can see. I need all the room I can get. So exercise 3, this reminds me of a geometric formula right here. 2 times 3 to the I minus 1. Let's go ahead, and I'm actually going to skip the generating of all the terms. I'm just going to sort of do it by myself on my own right here. What I think I'm going to do is I'm just going to start plugging in and see what the values are and just write it as a summation down here. The very first value of our index is a 1. Plug in 1, subtract 1, you get 0. 3 to the 0 is 1, and 1 times 2 is 2. The first term in my series is the value of 2. Plugging in the next value, the next index would be 2. We're going to, remember, start with 1, end with 5, plug these in, and come up with our series. Plugging in 2, take away 1 is 1, 3 to the first is 3, and 2 times 3 makes 6. This is geometric. It looks like I'm tripling. My next value, I'm just going to guess, is 18, but I want to confirm that. So term 1, term 2, plus term 3. So the index for the third term would be a 3. 1 less than 3 is 2. 3 squared is 9, and 9 times 2 is 18. Yes, this is geometric. I'm just going to wait for this to focus. Come on, focus. There we go. So our third term is 18. Our next term, plug in the value of 4 for the index. 4, take away 1 is 3. 3 to the third is 27, and 27 times 2 is 54. When does it end? It ends with our very fifth term. Plug in 5. 5, take away 1 is 4. 3 to the fourth is the same thing as 9 squared, or 81. 81 times 2 is 162. Add these numbers up together, we get 242. So the sum of this series is 242. Question number 4. The formula to the right looks arithmetic, and we'll do this one more time. It looks like I'm adding together 13 terms of an arithmetic series. So the very first term, I'd plug in the value of 1 goes in here. Negative 5 times 1 plus 25 gives me 20. Plus, and if I recognize this is going to be arithmetic, it looks like my slope, or rate of change, or common difference, is minus 5. Then that means the next term is 15, 10, 5, 0. So that's 1, 2, 3, 4, 5. Then plus a negative 5, plus negative 10, plus negative 15, plus, looks like I'm running out of space, negative 20. Let's see, I might be off my page already. So I'm going to write that negative 20 down the line, plus negative 20, plus negative 25, plus, now how many terms do I have? I need 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and my last term is negative 40. What we're going to next do is add these together. You might notice when I wrote this down here, I noticed that these two are going to cross each other out because they're opposites. We're going to have a couple of opposite pairs that I'm going to cross out. When I add these together, they make 0. That's something that's interesting. I'm going to need to remember that for a little bit later, maybe in our next section. It looks like I had a bunch of terms that I didn't cross out, like negative 40, negative 35, negative 30, negative 25, and 0, which really doesn't add anything to the sum. Adding these 4 terms that didn't cross out and cancel out gives me a value for my series, and that value is, let's see, we got negative 130 is what I think I found. So that evaluated series is negative 130. Getting close to the end for number 5. This formula I don't really recognize as arithmetic nor geometric, but it only has 4 terms, so let's generate them out. Plug in the value of 1. Now I have 2 locations to plug them in, one in the numerator and one in the denominator. So let's plug in and find the value of our first term. Let's see, the numerator will be a 2, the denominator will be a 3. So 2 times 1 divided by 1 plus 2 would be 2 thirds. That's our first term. Plus 2 times 2 divided by 2 plus 2. That's 4 over 4. That's a value of 1. Plus 2 times 3 divided by 3 plus 2. That's 6 fifths. And finish it. This last term in the series is 2 times 4 divided by 4 plus 2. So that looks like it's 8 over 6, which can reduce to be 4 thirds, and I think I'll take an opportunity to reduce that because I have 2 thirds over here. So now I have all these 4 terms in my series. 2 thirds plus 4 thirds makes 6 thirds. 6 thirds, also known as 2. So I have together these 2 terms makes a 2 plus a 1 plus a 6 fifths. If I made common denominators, I would change everything to fifths. It would be 10 fifths and 5 fifths, plus 6 more, I think is 21 fifths. So as a fraction, the series looks to me like it would be 21 fifths. Check my math out on that. I think we got 5 fifths, it would make 11 fifths, and then this would be 10 fifths, right? Looking good. This last one is a challenge. It says that we're going to start with the value of our first index is 1, and it goes all the way up to infinity. Is this even possible? More on that later. Why don't you challenge yourself and see if you can figure out what the sum is going to be approaching. Good luck!